Hello and welcome to the NXP Semiconductors and Future Electronics webinar on adding AI and machine learning with NXP's family of MCUs and processors. We have two fantastic experts on the call, JP Marcelino, Future Intelligent Solutions Regional Sales Manager, and Altaf Hussain, Edge Processing Segment Manager at NXP. I'm your organizer, Rashnika Fernando. Please feel free to type in your questions as you follow along, and we will answer them at the end during our Q&A session. You can type them into the right-hand panel of your GoToWebinar browser, or if you're on mobile, hit the question mark button on the top and you can type in your question there. If you want to learn more about incorporating NXP devices into your AI and machine learning applications, we'll post a poll at the end of the call and you can let us know if you want a follow-up call with us. So without further ado, let me hand it off to our presenters, JP and Altaf.
Hi, Rashnika. Again, thank you for the nice introduction there. For everyone here today, I just wanted to first off and say thank you guys for carving out some time to sit with us and to listen about AI and machine learning, as well as what we can do from an NXP perspective as far as enabling your solutions with their family of microcontrollers and processors. So just to really cover briefly what we're going to talk about today, we're going to cover a few topics. I know everyone today has quite a few different levels of understanding as far as AI and machine learning goes. So we'll cover just a few basics on the topic, just so everyone gets a better understanding of what's involved with creating AI and machine learning solutions. Then we'll cover a little bit as far as an introduction to NXP's processor families, which really will just highlight the types of devices that you can utilize for some of these AI ML applications. And then at that point, I'll hand it off to Altaf, who will talk about NXP's specific enablement from both a hardware and software standpoint for your AI ML solutions. And then we'll briefly touch on some machine learning examples at the very end, so you get a good idea of really the types of applications and solutions that you can enable with NXP's processors. So real quick before we get started, just wanted to introduce you to our team specifically a little bit. You know, Future Electronics is really a great global distribution partner for NXP. We work really hand in hand very well with NXP as far as promoting a lot of their products over a wide variety of different applications. The group that I'm a part of within Future is Future's FIS specialist team. We're one of probably 5 or 6 different, I guess you can consider them verticals, that supports a subset of Future's products for customers like yourselves. We really focus on Future's higher end products, which includes NXP's variety of different microcontrollers and microprocessors. So we really get involved with doing presentations like this for you guys today to help you guys really architect your designs and to get you all the way into production with a wide variety of different applications and solutions. Okay, so let's get started. And I wanted to just go over kind of what the difference between AI, ML, and deep learning is. AI has really become this catch-all idea where we're essentially trying to make our hardware and our products act more smarter or act more like a human. Machine learning is the subset of AI, which is this data-driven approach to achieving this. So we're really trying to feed our products and our hardware lots of data so that we can train it so that it can do all of these smarter actions on their own. Within machine learning, there's also something called deep learning, and that's specifically utilizing neural networks to process all of this data so that we can train those solutions to do all of these products and smarter actions with them. So something to keep in the back of your mind, deep learning isn't really the only method to creating algorithms for AI ML solutions. But from an edge standpoint, it's become a pretty commonplace method to do AI ML. So we're going to focus on that for the majority of this presentation, but just something to keep in the back of your mind as we kind of talk about AI and ML during this presentation. Okay, So when I talk to people about AI and machine learning and when they get started trying to learn about the topic a little bit, I try to emphasize two things with them. The first is to, try to get a good understanding of the problem you're looking to try to solve or the application you're going to do. There's some types of applications that really fit nicely from an AI and machine learning standpoint. They involve things that are either vision-based solutions where you want to detect different types of objects within an image, or being able to count the number of people within an image or to track their gestures. Audio type is also a pretty typical application where you want to be able to recognize custom phrases that you're speaking to from an audio standpoint. And then there are also solutions that revolve more on time series type of sensor data. So those are applications that revolve around doing things like anomaly detection or predictive maintenance. The second thing I like to emphasize is to really understand whether or not machine learning would be a good fit to solve these types of problems or create these types of applications. On the previous slide, I really emphasized the fact that this is a data-driven approach to AI. So you really want to make sure you're starting off with a good relevant set of data to train and create your solutions. Is this going to be something where you can utilize open source data to just detect, common objects or classes for a given solution? Or is this something where you'd have to utilize more proprietary data, for example, to maybe detect your own specific product within an image or to detect your own custom key phrases for a audio application? And then the second half to that question is really more of an understanding from an architecture standpoint. So just want to make sure you understand where this data is really coming from, and then how much time do you really have to process that data and make some kind of inference or prediction at the other end? Is this something that you have to react to very quickly, or do you have a few seconds or even a few minutes to process all of that data to ultimately make some kind of prediction on the other side? Okay, given that, we traditionally see two types of AI and machine learning systems at the edge. Now, the row on the top there that you see is what most people think about when they hear AI and machine learning. Now, that's utilizing either some kind of image sensor data or audio data. So think of things like a Google Home or an Amazon Alexa, and passing that data through some kind of neural network to process it, and then ultimately make some kind of prediction or inference on the output side. So these are applications for things like facial recognition, object classification, or being able to recognize different key audio phrases. The second type of system that we traditionally see are more time series sensor dependent solutions. So again, think of things like audio data, but also think of things like strain gauges, vibration data, accelerometer data for motion, and then passing that again through some kind of a more simple neural network or even just a pattern classifier, again, to make some kind of prediction on the output side. So this is where you see more of those anomaly detection or predictive maintenance type of AI machine learning solutions. Okay, given those types of systems, how do you get started from a model creation and training standpoint? Again, I can't stress this enough as far as having a really solid data to get started with. It can be as simple as just being able to differentiate between two different types of objects, in this case, a cat or a dog. But you really want to make sure your data is properly labeled with the correct objects that you're looking to classify. You then take that data and bring it to one of the many different machine learning frameworks that are out there. And NXP does a really good job with supporting a lot of these different options. So it's just making sure that if you've got a specific microcontroller or microprocessor in mind, just to make sure that the software enablement supports that machine learning framework you have experience with, or kind of vice versa if you already have an experience with a TensorFlow Lite or an Onyx, for example, just to make sure that the device you're targeting would support that all the way through from an enablement standpoint. Okay, from a training and inferencing point of view, traditionally we've seen a lot of this done in the cloud, right? All of the computational capabilities have been there for a very long time. But now that we've got microcontrollers that run as fast as they can, we'll have later on during the presentation, and even microprocessors that are more than capable. They have multiple cores running within them. We've really started to see this trend to move a lot of the inferencing to the endpoint or to your end device. So you can have some combination of the two, where you can have an initial amount of inferencing at your end device so that you can minimize the amount of times you have to go back and forth into the cloud to do your inferencing, or have complete solutions where they're fully disconnected from the cloud and do all of your inferencing at the edge without having that need for connectivity. Okay, this will be a good just point of reference for you guys, especially for those that don't have as much experience from an AI and machine learning standpoint. This just goes to show you and highlight a lot of the different types of applications that you can really get started with today from an AI machine learning use case. Again, like I mentioned before, they really revolve around specific types of sensors to use for doing things like object detection and classification, different types of audio applications, or different types of time series sensor data solutions. Okay, so again, I mentioned earlier on that kind of deep learning and neural networks has been really a common method to implement a lot of AI and machine learning algorithms, especially at the edge. So we'll take a look at this in a little bit more detail, and we'll use this image classification process to understand a little bit more of what's going on in each of those pieces. Again, I talked about earlier on the emphasis for training your solutions and having really good, well-prepared, relevant data to create a solution that you can train to some amount of accuracy before you deploy it onto your hardware solution. When you've got something that's deployed, a few things happen inside the neural network. First, we're always starting with some unknown input, right? In this example, we're trying to classify different types of animals seen in an image. You and I can see that it's a picture of a dog, but we're just utilizing the neural network to try to make that prediction for us. Within the neural network, a few things happen. The first piece of the neural network is what you could consider a feature extraction stage. And essentially all that's doing is it's highlighting a variety of different curves and edges within that input image to correlate them to certain features that the neural network's been trained to recognize. So in this instance, we're just highlighting different pieces of the inputs to pull out things like the tail of the dog, for the example, or the feet or the face of the dog. We take all of those features and pass it on to the second half of the neural network, which is the classification stage. All that's happening in the classification stage is lining up those features that you've extracted out of the neural network to only try to use those to make some kind of prediction that it was trained to do. So in this instance, we're trying to look at the tail or the foot or the face of the dog and try to predict what animal that is. In this instance, the neural network is going to tell us that it thinks it's 90% a dog versus 10% a wolf in this example. So again, just to kind of summarize, we've got a few stages here as far as deploying a image classification solution. The training stage, which is pretty common to all types of applications. Once you've got a solution that's trained to the accuracy you want it to run on, you've got it deployed on a set of hardware where you start off with some kind of unknown input to extract some features to make some prediction on the output side. Given all of that, there's really a lot more that's involved as far as neural networks goes, right? And we're kind of transitioning a bit here to more of a vehicle classification example here. But kind of similar things are happening where all of these columns here represent a variety of different matrix calculations which do the feature extraction from your input image. So when you look at kind of the first few columns here, you can really start to see that some of the images highlight things like the hood of the vehicle or the front of the vehicle or the sides of the vehicle. And then you kind of pass those along through multiple stages. What you'll notice is sometimes the images tend to look a little bit more abstract, but just keep in the back of your mind that those really just represent the features that the neural network has been trained to extract out of the input image. And then again, this FC, or fully connected layer at the very end of the neural network, really just represents the neural network trying to make its prediction for you. So it's just going to give you some percent value for all the different types of classes that it's been trained to try to detect or make a prediction against. Okay, given all of that, and kind of the nice thing to keep in the back of your mind is 9 times out of 10, you're not starting from scratch with a lot of these solutions. There's lots of architectures that are already out there that lots of people have used open source data to train to some amount of accuracy. And NXP has already taken a lot of these different architectures and created lots of different reference designs and demos that you can use as a great starting point for your given designs. We'll talk about a little bit more detail, kind of the enablement that revolves around all of these. But again, just to reiterate here, you're not going to be starting from scratch and having to create a lot of those layers and calculations and models from scratch. You can really utilize a lot of what's already out there and what NXP has already put together from a demo and reference design standpoint to give you guys a good head start to create your own custom applications. Okay, and then lastly, I wanted to briefly touch on transfer learning. And this is really the whole idea of being able to take an architecture that already extracts certain types of features very well and to retrain that solution to care about the classes or objects that you're looking to implement for your own specific application. Kind of the really common example of this is from an audio standpoint, where if you find a architecture or solution that kind of demos pretty well, being able to recognize some generic key phrases, you can take that same demo and solution and just retrain that classification portion of the neural network to care about the custom phrases that you'd like to implement into your own end application. You can also do things like from an object classification standpoint where, say, there's a demo that utilizes an architecture that can detect 20 or so different objects from an image classification standpoint. And you want to create a solution that walks up to some kind of device and only lets you know if a person is walking up to it holding a cell phone. You can retrain that solution to ignore the other 18 or so objects that that demo looks at and only care about the 2 or 3 objects that you would really want to implement in a given application. Okay, from an introduction standpoint, I like to end it there because the whole idea of being able to do transfer learning and retraining a solution gives us a nice lead in as far as what NXP has from both a hardware standpoint and from an enablement standpoint, from an AI and machine learning point of view. So what I'll do is I'll just briefly highlight the different processor families that NXP has and what they've put together to really give you guys a wide variety of solutions to use. This chart right here just really highlights the wide variety of different processor options from NXP. They've got a variety of different families that are more Cortex-M core based with the LPC, Kinetis, and S32K families. They've got this group of what you could consider crossover microcontrollers or processors with this I.MX RT and I.MX ULP family of devices. They kind of give you the best of both worlds as far as some of the capabilities from both a microcontroller standpoint and from an application processor point of view. And then you can scale up as well to more specific Cortex-A core types of devices between the S32 family, the I.MX family, and the Layerscape family of devices to really give you a wide variety of capabilities from an application standpoint, whether you're more concerned with things like audio, graphics, or even networking capabilities. Okay, because NXP has this wide variety of processor solutions that you can use, they're really giving you a variety in terms of performance within each device family. So you have the capability of really getting 5 to 10 times improvement with each jump from each family of processors. So you have the ability to start off with maybe a more simple solution that's just more processing still images or kind of lower resolution applications. And then if you need to scale your performance up a little bit because, say, for example, you want to get into more live video streaming and doing AI ML with those types of solutions. You can scale up to more of an I.MX RT family or even an I.MX or Layerscape family of devices. And then on top of that, you've got the ability to scale even further with either application processors that have built-in neural network engines or even add-on accelerators from things like Google TPU as well. Okay, so let's just briefly talk about each family from the previous slide. Let's start with the I.MX RT series. This is that M7 class of microcontroller that's considered more of a crossover family of processor where you get the best of both worlds. You get a very high-speed M7 microcontroller that can run anywhere up to a gigahertz in terms of speed. And then you've got the flexibility just within this family alone to really scale up and down if you're looking at options to give you higher performance, for example, or you want some additional graphical and security capabilities, or if you're even looking for a family that's specifically focused for audio type of applications, you've got that flexibility within the I.MX RT series of devices. Next up, kind of going up that spectrum, is the I.MX family of application processors. Now, again, it's kind of similar to the I.MX RT. We've got a wide variety of solutions here. So even if you're looking at, let's say, for example, a 32-bit architecture, you've got a lot of different options within the I.MX 6 family and the I.MX 7 family of application processors, where if you need things that are a little bit more focused from a graphics or a connectivity standpoint, you've got a variety of different options there. Now, if you need to scale up in terms of performance, there are 64-bit options as well within that I.MX 8 family of devices. Again, if you're looking for things that are either more safety focused, or if you're looking at devices that are more capable from a graphics or CPU performance standpoint, again, you've got that ability to scale up and down as kind of your performance requirements change. I did want to highlight one device here, and that's this I.MX 8M Plus, which right here is a little bit more of a sneak peek. I believe it's going to be released later on towards the end of this year. But this is a family within the I.MX application processors that also includes a machine learning accelerator built into the device. So not only you get a lot of the capabilities that you would traditionally get from an I.MX family of processor with all of the different connectivity options, all of the graphical capabilities, but you also get 2.3 TOPS of performance along with it. So if you're looking at different types of vision solutions that you would like to have quite a bit from a computational standpoint, this would be a nice device to look at, especially for vision-based solutions. And then lastly, I did want to touch on the Layerscape family of processors as well. Again, this family has quite a variety of options, so you get that same scalability within this family of processors. So they range anywhere from a single A53 core that's running at 1 gigahertz all the way to the higher end of the spectrum, which is an 8-core or 16-core A72 application processor. So again, you get that same scalability within just this family of devices. You also see some pockets of different options here and there where you have, say, for example, a flavor that has 1 or 2 A7 cores if you want to stick with the 32-bit architecture. There's also flavors that do come with an integrated GPU and a TS-Sense switch. So depending on your application and performance requirements, again, same thing like the other families here, you've got that flexibility to scale up and down as needed. Okay, on that note, I really just wanted to summarize with this where, NXP really has this wide variety of processor options, whether you're looking at just doing more simple data acquisition or analytics. You've got a variety of different families amongst all of those different processor options to look at. Then you can scale up as needed if you've got some more heavy-duty video or image processing, if you want to run Linux or Android, or even really large-scale solutions that require multiple video streams, multiple algorithms to really do some high-end stuff. Okay, on that note, I'll hand it over to Altaf. We'll talk about NXP's AI and enablement solution.
Okay, thanks, JP. And Good introduction, appreciate it, thanks. So I'm going to talk about enablement, as JP said, and also some actual use case examples at the end as well. So we'll start off this slide, and there's a variety of different ways that we enable our solutions, for you guys to consume our technology. So one is in the form of turnkey solutions. So what we're talking about here is a kind of a voice-enabled solution. This has Alexa voice services, so it's a full turnkey hardware, software solution that comes fully certified. So you can really go to production with the device, or you can make changes. You get source code, you get the source files for the design, and you can kind of customize for your end application as well. Also, from a device perspective, this is going to be enabling kind of more solutions on our next generation devices as well. So I.MX 8M Mini, and then I.MX some of the additional I.MX RT devices. So look for additional turnkey solutions that'll be coming shortly as well. And then the other is in the form of enablement. So EIQ, this is kind of our edge intelligence at the edge, and this is the way we enable machine learning applications on our processor technology or microcontrollers as well. So this is basically, supporting common frameworks that exist in the open source community. So, different network, in terms of neural networks and models that are available. So you can basically take those as is as part of our development environment, whether it's MCU Expresso for the microcontroller family, or kind of the Yocto environment for the I.MX family, and you can compile those in and be up and running with those models fairly quickly to enable those on any of our devices. And then we have a third-party ecosystem as well. So there's hardware solutions that are available. One is the Coral development board. So this has an I.MX 8M on there, along with a Coral TPU as an AI machine learning accelerator. This comes as a module, so you can design your own carrier board, and you can plug this module in, and you can kind of customize your different I/O requirements depending on what kind of data you want to bring in and what kind of outputs you need to control various different systems. And there's already a whole host of software enablement on that module that's available that you can leverage for kind of AI machine learning applications as well. And then we have partners that support Alexa voice services, as well as development tools for AI machine learning applications as well, and Ozone is one of those. They provide a tool chain which will take you to the full kind of design flow, process, and they target all the way from our microcontroller family that's using, the M cores, and basically optimizing for a small memory footprint, as well as performance on those smaller cores, and scaling up to, the I.MX devices and Layerscape devices that have the Cortex-A cores available as well. And then lastly, edge scale. So for most of these AI machine learning applications, one thing to be aware of is that there's a lot of innovation going on in the community. In the open source community, every few months, every 6 months, you'll see kind of exponential improvements in capabilities, with different optimizations being available to increase the performance, add more functionality. So you need to be able to update these models in your end systems in an easy way. And edge scale is basically a kind of a secure, device management and application deployment platform. It can be hosted in a public cloud or a private cloud, or even locally on a kind of a server or a PC platform. And it allows you to authenticate your end devices to make sure that you can securely communicate with them using security certificates, and then you can deploy secure signed images as applications to those units once they're authenticated. And this supports, the Layerscape and I.MX devices today. And we've also pushed this technology out to the open source community. So this is available in GitHub, and you can take this as is and deploy this, as a solution today, or augment it and supplement it in any way that you like. Or you can work with NXP and software services, to kind of customize this for your end application as well. This is, I'm not going to go through this in detail, but this is talking a little bit in more detail about the turnkey solution and all the different pieces of collateral that are available. So source code, all the design files, all the certifications. So everything is available, on this particular platform today. And then from a machine learning software, models that we support. So this kind of gives you a reference that's kind of an easy, to look at from which devices we have, what different IP in terms of CPU cores or other, IP that you can take advantage of from an AI machine learning perspective that's available on those devices, and also what frameworks are supported on top of these devices as well. This isn't an exhaustive list, but it gives you an example of the most popular frameworks that are out there. So SimSys from ARM, mostly for the microcontroller family. This is a library of kind of optimized kernels that's designed to run on Cortex-M cores and accelerates various different functions for neural network processing. TensorFlow Lite, also TensorFlow Lite Micro for microcontrollers. Glow is a new kind of a neural network compiler support that we've just added as part of the EIQ framework as well. We'll talk a little bit about that later. And you can see across the board, we support most of these models depending on the end device on Cortex-M. And if they have other IP like DSP, GPU, NPU, then you can see what's supported there as well. So EIQ, just to get kind of a level set, this is basically, as I mentioned before, a development environment. It's a collection of library that really gives you the tools for building machine learning applications. So it's designed to work with our microcontroller and applications processors. So it's part of the development environment, for example, for the microcontroller family, the MCU Espresso, and also for the Yocto, Linux BSP that we deliver for the application processors. So we have different models and tool chains like the Glow compiler that are supported as part of that. So you can easily compile those in and get up and running fairly quickly. On the Layerscape products, we support this as part of what we call our Layerscape SDK. The last release was at the end of April. And it's also got, similar to the I.MX family, various different models and inferencing engines that are supported as part of that. And we'll talk a little bit in more detail about some of these solutions later when we talk about some of the examples and platforms that are available as well. And there's a supporting documentation available on the NXP website on EIQ. There's users guides, release notes, and demo users guides, etc., that you can use, to learn more about EIQ and how you can use this, to develop AI machine learning applications on NXP solutions. So this is kind of a development, environment in a little bit more detail. So you can see here at the bottom layer, we have the silicon-specific parts here. So from the Kinetis, I.MX family, as well as the I.MX applications and Layerscape processors, the various different IP that's available. Then you have the hardware abstraction layer, which is basically where we can run things like OpenCL, OpenVX, OpenGL, those kinds of things to take advantage of the different hardware IP that's available. And then you have the inferencing engines that are available, and we support open source inferencing, common frameworks that are out there. So, OpenCV, Onyx runtime, those kinds of things are available. And Glow, as I mentioned, as a neural network compiler technology. This is kind of the preferred compiler for the PyTorch, community. So if you're using that as a development environment, this is by default their preferred compiler. And this basically gives you optimized code that translates, your high-level machine learning models directly into machine code that's running on a particular device. So it's more optimized for performance rather than going through some of these, abstraction layers that you go with through some of the other tools. And then obviously you have your applications on top, whether it's video or image-based applications for object detection, or voice recognition, or time series, like some of the ideas that JP talked about earlier. And this is a little bit more specific to Layerscape. So this is talking about how we enable some of the machine learning applications and inferencing models on the higher end Layerscape processor family. So here you can see we can support a whole host of different models for facial recognition, object detection, gesture detection, and there's various different applications that you can add. This is not an exhaustive list, and this can be from an application perspective, any kind of industrial safety, control application, video surveillance, robotics, automated guided vehicles like AGVs or mobile robotics. They require a lot of these different capabilities, and they require perhaps multiple frameworks or multiple inferencing engines to be running on the processor at the same time as well, depending on the problem that you're trying to solve. So the Layerscape devices basically have a wider support for different distributions of Linux that's available. So we can support not only Yocto, but we can support Ubuntu, we can support Docker, we can support KVM from a virtualization perspective. So using either Dockers or KVM as a virtualization environment, you can basically add, multiple frameworks and multiple inferencing engines on top of these devices, and basically scale up and down as well. Docker, for example, once you developed it, let's say on a dual core device, on a Layerscape device, that same Docker that's now running on a dual core will run on a 16 core device unchanged as is, so you can scale up and down in terms of performance. And then also if the CPU performance is not sufficient, as JP was mentioning earlier as well, we do have the ability to add external accelerators for AI machine learning. These can be connected through either a USB interface or a PCIe interface, depending on what type of device and what type of modules might be available. And these can give you, significant improvements in performance as well, depending on the kind of, inferencing performance those devices can support. It can range anywhere from maybe, 10x to 15x performance improvement versus running that same model on a CPU platform. So a lot of different options there. And then on the right-hand side here, you see, some of the things that have to be done in the cloud. So basically, on the silicon side, on the Layerscape side, or any of the other devices, we're assuming you've already done the model training, you've optimized, the inferencing engine, then you basically are converting it to run on a particular device, on a microcontroller or an application processor. But a lot of that training happens in the cloud. The new tools like, Amazon's, SageMaker, Google AutoML, where you do your model training, you have all your data set and you train the model, and then you have something like EdgeScale or something like it that allows you to securely deploy that application now that's been optimized in the cloud for these particular devices. So here you do the device management, application management, and containerization to create that Docker container that will be deployed on these devices. And then this is just a little bit more detail on the third-party kind of ecosystem. So we talked about the core Coral board that's available for the I.MX family. This is the A10 plus the Coral TPU, and then at the bottom there you can see kind of the add-in modules that are available for the Coral TPU as well. There's a USB module as well as an M2 module, and that can be plugged into any of our processors to accelerate inferencing as well if the module is not sufficient for the CPU performance that you need. And then some additional partners that we have on the third-party software ecosystem. So we talked about Ozone, but we have partners Envision, Pilot AI, Irida Labs, so that's available. And then open source software. And when you saw in some of the previous slides, we support a lot bigger ecosystem than what we've mentioned here. But this is kind of the standard OpenCV, Keras, Caffe, TensorFlow, YOLO. These are supported across our platforms. And there's a whole host of additional capabilities from an open source perspective that we support on our platforms that's not listed here as well. So a little bit about EdgeScale and how this can be used, and there are equivalents available in the from other vendors as well from a software perspective. But I would really recommend that you need something like this if you want to keep up to date and keep the model updated on your edge devices as you go forward, because you're going to be learning as you collect data on these products. Maybe you want to use that data in the cloud to retrain that model and redeploy it to improve the accuracy of the model over time. So this kind of tool allows you to do that. And the way EdgeScale basically works is there's a couple of different pieces to this. One is the authentication of the edge device. So you need to be able to program secure credentials at the manufacturing stage in your products, and we provide mechanisms for you to be able to do that, to provision security keys during the manufacturing process. And as you manufacture those products, you create a manufacturing record for each of those devices that you manufacture. and that data is then stored in the AdScale portal. And basically, when you ship a device to your end customer, they would register that device against the portal, and the device would authenticate itself against those manufacturing records that were created. And if those records match in terms of the unique ID for the box and the security keys, then it will proceed to the next step, which is the enrollment, the provisioning, allow the firmware updates and the applications to be deployed on the box. And if it's not authenticated, then basically it's just going to be a brick. It's not an authentic device that belongs to you, that you would have shipped with your security keys. So nobody's going to be able to use that device. The other part of AdScale is the continued monitoring of the device. So, one is you can continue to collect data and update the model in the cloud and redeploy it at a later time if you need to. The other is the monitoring of the health of the edge device. So you can have mechanisms built in to detect that maybe something is going wrong and you want to do some kind of preventive maintenance on the unit. You can do over-the-air firmware updates as well. And there's also a mechanism, since if you're going to use containers to deploy applications, you can almost have an application store where your customer swipes a credit card and they can download a new service, assuming that you have the headroom available on the CPU to be able to add those applications after you ship the product as well. So a lot of different capabilities that AdScale can enable from a solution perspective. Okay. So just to go through a few examples on how our products can be used and how potentially customers are using our products. So the first one is this new device that JP talked about, which is the I.MX A10 Plus. This is the one that has the neural network processing engine accelerator built into the device. It also has various different other IP that's very useful for a fleet management kind of driver monitoring application. It's got multiple camera input, so you can have a camera that's looking outside and looking at the traffic, the weather, making sure that you're driving in lane. You can have a camera facing in the cab, look at driver attention monitoring and have some kind of a warning mechanism if the driver is feeling drowsy or those kinds of things. And you can record that information locally as well as send it to the cloud or a secure operations center. And if you're not connected to the cloud, it can be stored locally and then streamed later as well. But this gives you a record for insurance purposes, for kind of driver training purposes, for safety and improving the efficiency as well. And it's got a bunch of other IP on this processor, like the ISP, where you can automatically resize the images, to feed your neural network as well. So a lot of capabilities on this device that you can utilize for kind of like fleet management, driver monitoring type applications. The next one here is kind of like mobile robotics, or AGV. So this is kind of showing a high performance processor, a 4-core Layerscape device in this case. And these you'll see typically in big kind of Amazon warehouses where people are moving inventory around for shipping or for storage. Even in manufacturing applications, you see these as well. The traditional AGVs have typically been kind of following a fixed navigation path, so they're following like a magnetic strip or some kind of laser guidance kind of system to basically find their way around a warehouse. But the kind of newer generations are adding more intelligence and AI and machine learning, so they can automatically map the environment, they can detect objects with radar and cameras, and they can avoid those objects and go around them. So these are more intelligent and can be reused and redeployed fairly easily as well. So this gives you an example of how you may map this kind of application to a Layerscape processor, both from an I/O perspective. So bringing in radar maybe through an Ethernet interface, cameras you can bring into either a USB or an IP camera through Ethernet. You can have wireless and wired connectivity in terms of Ethernet and Wi-Fi, and then you have multiple cores available to process that data that's coming from these various different sources. So, to the radar capture and classification, the video capture and video classification, and then the networking applications and stacks to manage your Wi-Fi and the wired Ethernet connectivity, from a security firewall and all the communications you need to manage as well. So this is another example of how to use our processors. So finally, this is the same device that I just showed you on the previous use case, but this is kind of like an edge compute platform where we've enabled quite a few development environments in terms of different Linux distributions, OpenWRT, Linux containers, like I mentioned, Debian releases like Ubuntu, CentOS, KVM for virtualization, and we also have multiple different AI machine learning frameworks already running on the platform as well: Yoler, TensorFlow, TensorFlow Lite, OpenCV. So all of these are running on there, and this also comes with and without kind of AI machine learning accelerators. The -TP version that I'm showing here ships with a Coral TPU that's inside the box as well. So you can try out your frameworks, on the CPU, on the TPU as well, and kind of see what's going to give you the best performance. This system also gives you a lot of statistics on the CPU usage, the memory usage, all the different resources within the system. So you can use that data to kind of determine which devices will best, solve your problem from a performance, power, cost perspective as well. And there's a URL here where you can get more information on this platform on the NXP website as well.
Hey, Altaf, I just wanted to briefly add on to this. So this edge compute platform and then some of the turnkey solutions from NXP as well, both Future and NXP, we can work together to show off these demos live for you guys. So all of the team within FIS has a lot of these evaluation platforms and demos that we can help showcase for you guys as part of a follow-up meeting as well.
Okay, I think that was the last slide. Rashika,
right.
you want to open it up for
Yes.
Q&A?
Absolutely. So first, thank you, JP and Altaf. We're going to move on to the Q&A portion of this session in a second. But first, I'm going to put up a poll for us. There you go. You should see it on your screen. So for folks, if you want to have a follow-up call incorporating NXP devices into your AI and machine learning application, go ahead and click yes, and we can set up a short call for you with JP. And then, while I leave this poll up for a little bit, as a reminder, if you want to ask a question, you can just type it into the GoToWebinar panel or app. We had a couple of questions come in. So let's go over a couple of them. First, how do you determine what device is suitable for a particular AI ML application, like building control, industrial safety, or smart agriculture? How do you pick which one?
So,
yeah,
go ahead, JP.
Okay, I'll start and you can elaborate too, Altaf. So typically what I'd like to suggest just from a general starting off point is to understand a couple things about your application. They kind of revolve back with those few questions as far as what kind of data you're trying to process, and then how much speed you're looking to use as far as creating this application. So say for example, you want to do an application to monitor different types of sensors. How much data are you trying to process? How fast do you want to react to it? That tends to lead you to kind of a good starting point as far as maybe looking at a microcontroller that's doing some kind of reference demo that's pretty similar to your application. You'll be able to see what kind of performance that microcontroller is running on, and then kind of scale up and down as needed as far as maybe looking for a good starting point as far as a device goes.
Yeah, the other thing I would add to that is, what kind of I/O do you need, right? I mean, if this is going to be image or video-based data, do you need, MIPI, CSI type interfaces to bring that in? You need to do any kind of video encode, decode, or resizing within the device, because typically when you think about AI machine learning applications, you don't think about some of the pre-processing and post-processing that you have to do outside of the actual inferencing performance that you need as well. So take the whole kind of system into consideration from an I/O perspective, because you need resources and CPU performance to do that processing as well. And to a certain extent, you can look at the I/O, you can look at the kind of performance like JP said, and kind of get a rough idea of which devices you may target. And then it's really more experimentation in terms of which model is going to best solve your problem. And this really is experimentation, because there's no right or wrong answer here. You have to try different frameworks and see which one is going to give you the best fit for your application, and which is going to give you the best performance. And that can vary quite dramatically as well. So once you do that, go through that flow, you'll get a better understanding of which devices kind of fit that application.
Great. Next question, can you describe a bit more about the machine learning hardware acceleration core within the I.MX apps processors, probably the I.MX 8M+? What is the architecture, and is this like a GPU?
No, it's not a GPU. This is basically an inferencing engine accelerator. So it's able to accelerate, inferencing engines like TensorFlow Lite, those types of things. So it's really agnostic to, a lot of the different, inferencing engines. It's a way to kind of do processing of these different layers in parallel on this kind of IP. And we provide tools that really allow you to take these open source models, like the ones I talked about during the EIQ discussion, and map those to this neural networking processor to accelerate the actual performance, rather than running it on the CPU core or the GPU. And it will give you significant performance improvement. Like I said before, the accelerators tend to give you anywhere from maybe 10x to 15x performance improvement versus running it in software only on the CPU cores.
Great. JP, early on you mentioned predictive analysis. Can you talk a little bit more about the kind of statistical algorithms that you use? Is it like your classification model or regression model?
Yeah, so really there's no kind of one size fits all when it comes to doing things like predictive maintenance. Like I mentioned before, right, there's tons of different kind of algorithms, even from doing things as simple as like decision trees and really simple things like that. So it all really depends on, again, the types of sensors that you're looking to monitor and do your predictions, and doing things like k-nearest neighbor. And so there's lots of different ways to kind of skin the cat with this. And it'll really be dependent on, what kind of sensors you're looking at, for example, to kind of detect the different anomalies in your system, and to ultimately try to find an algorithm that kind of best fits the type of sensors and the number of sensors you're looking to use for a given solution like that.
And if you look at some of the work that we've done within NXP, I mean, we've used SVM, which is your support vector machine learning model for some of the anomaly detection. And it may not be the only way to solve, kind of an anomaly detection problem, but that's, an example of an algorithm that you could use for that application.
Great. Next question, Altaf, perhaps you can answer this, and then JP, you can chime in. What platform would you recommend for someone who wants to get started to evaluate and learn about AI/ML?
So I think, the platform that we showed earlier, that, the Freeway LS1046 is what I would start with today, because that gives you the ability to kind of try out different frameworks on the CPU. It will give you all the statistics that you need to kind of size the performance on the CPU as well. So even though it's a 4-core device, it will tell you how much CPU utilization you have. And from that, you can determine if it could run on a single-core device, or maybe it requires a 4-core device. And then you can also have the AI accelerator there as well. So if you offload that to the accelerator, then what does the CPU utilization become? And you can make that trade-off of, do you need an accelerator or not to achieve the performance that you're looking for? Does it meet your cost, performance, power constraints? So this is an easy way and an easy to use platform. And as JP mentioned earlier, there's a lot of AI machine learning demos and software that's already running on this platform that you can use as a starting point. So that's what I would use today. I think, come maybe 6 months, from now, the I.MX 8M+ will be available as well. So that's another platform, once that launches to the market, that has built-in AI machine learning capability, also has the built-in kind of video and image kind of processing IP available as well, would be another platform depending on your application that would be a good fit, maybe starting sometime in first quarter or second quarter next year.
Yeah, just to add on to Altaf's point, this platform is a great platform to get started with. It's definitely something that, by all means, if you want to start to play around with it, reach out to us. We can help you get started, even show you guys some demos initially through a follow-up meeting or even in person when we get to that point, just to give you an idea of the types of demos that are running on this platform and to see if they get you close to a good starting point as far as the type of applications you potentially want to implement.
Great. One more question. Altaf, I think when you were showing the EIQ slides, one of them mentioned Glow. Is this part of Facebook's new implementation that isn't quite released yet?
No, so we're actually going to be, I think, releasing it in a matter of a few weeks or so. So it's fairly new. It's going to be part of EIQ, and it's really a way for us to provide improved performance for our devices. It can give you significant improvement because it generates direct machine code that will run on our IP, and it can also target different IP within the device as well. So like the GPU or some of the DSP technology that we have. For example, on the microcontroller family, we have this Hi-Fi 4 IP that's in there. You can even use that because primarily, AI machine learning algorithms are doing mathematical operations, and you can do that more efficiently kind of in a DSP-like, architecture. So it can give you that Hi-Fi stuff, can give you significant improvements in performance as well, even though it's not dedicated neural networking processing IP. And we've done some work internally already, obviously, since that we're going to be releasing this very shortly. So this is coming and is part of EIQ, and it's coming very shortly.
Great, thank you. So we have come to the end of our time for this webinar. Thank you everyone for joining, and a huge thank you to JP Marcelino and Altaf Hussain for your time and expertise. We will be posting this. Yeah, thank you. We will be posting the session's recordings and any questions we didn't get to with answers on NXP's web and Future Electronics YouTube page. It may take a few days before you see it online. Thank you so much, JP and Altaf.
Thanks, everyone. Have a good rest of the day.
Have a good day.
Thank you. The webinar is now ending.